Hello, this is Weal Anawysis Wednesday, part 3. I have done every exercise in chapter 1, and I feel 100% solid about a good most of them. There's like one that I feel like is good, but maybe is not complete in a sense. Well, I'll get to that when I get to that. If you don't understand anything that you see on your screen right now, I would recommend that you go watch What You Need for Weal Anawysis Wednesday, Chapter 1. After I beat this chapter like a video game, after I complete this chapter, I am going to release... The next video is going to be going over what this book says in Chapter 2, which is all about cardinality of sets. And that's going to be really fun, because we didn't really go over that in any kind of rigor in any of my real analysis classes. We maybe like skimmed a proof that the reals are uncountable, but we didn't really do much with cardinality. I'm excited for that, but today I am going to be finishing chapter 1. So let's hop to it. We're starting out with 1.27. For each item, compute the requested supremum or infimum, or explain why it does not exist. Provide your answer. First, the supremum of A. A is defined as the set of -1 to the n over n, such that n is a natural number. And that's just going to look like the alternating harmonic sequence, starting with -1. So -1 to the 1 is 1, -1 squared is 1, -1 cubed is -1, and so on and so on. It alternates -1, 1/2, -1/3, 1/4, -1/5, 1/6, etc. So, the supremum of this set, what is it? Well, if we look at the terms, the first few terms here, it looks like 1/2 is the biggest term, and then they just all get smaller. So we would like to show that 1/2 is the maximum of A. And as we may know, if the maximum of a set exists, then it is equal to the supremum of that set, so that will be done. Okay. Oh, actually, you know what? Looks like I didn't do that. Looks like I straight up proved. Okay. All I proved was that 1/2 was an upper bound of A. And since it's in A, then it has to be the supremum. Okay. So we first note that for any natural number, n is either even or odd. If n is odd, then -1/2 to the n over n is smaller than 0. So don't have to worry about any of those terms. The even terms, however, might cause us an issue, because -1 to the n over n is going to be greater than 0. So if we can manage to show that 1/2 is at least 1 over n for any even n, we'll be done. 2 is indeed the smallest even natural number, and we know that if k and m are both positive, we'll say those are natural numbers. If k and m are both natural numbers and they're both positive, then if k is less than or equal to m, then 1 over k is greater than or equal to 1 over m. That's something we know. Since 2 is the smallest even natural number, for all k in n, for all even k in n. 2 is at most k. So that means 1/2 is greater than or equal to 1 over k. So for all even terms, 1/2 is greater than or equal to -1 to the n over n. So 1/2 must be an upper bound of a. Any other upper bound of a is not less than 1/2 because 1/2 is in a. So 1/2 must be the supremum of a. Done. Next problem. Well, not next problem, rather, but next part of this problem. This is still part of 1.27. Fix a real number alpha between 0 and 1, open interval. Find the infimum of b, where b is defined as the set of all alpha to the n, such that n is natural. I'm just going to assert up here that inf b equals 0. 0 is a lower bound of b, and then I prove it here. 0 is a lower bound of b because 0 is less than alpha implies 0 is less than alpha to the n. To see 0 equals inf b, let beta be greater than 0. And I went ahead and I drew a little picture here. If we multiply alpha by itself and alpha is less than 1, it's going to keep getting smaller and smaller and smaller until eventually some alpha to the n is going to be smaller than beta. And that will mean beta is not a lower bound of the set, which will then prove that 0 is the infimum. So we want to pick an n big enough that alpha to the n is less than beta. Alpha to the n is less than beta if and only if the log of alpha to the n is less than the log of beta, if and only if n log alpha is less than log beta, if and only if n... Now this is a little bit tricky because alpha is in here. Log alpha is negative, and when we divide both sides by this negative number, we have to flip the sign, or we have to flip the inequality. So if and only if n is greater than log beta over log alpha. This is just log beta over log alpha is just a real number. So by the Archimedean property, we can pick an n greater than this real number. Thus, beta is not a lower bound of b because there is a natural number n such that alpha to the n is less than b, meaning an element of b is less than beta. Thus, 0 is the greatest lower bound of b. I might try to prove alpha less than beta implies log alpha, or I might try to prove a less than b implies log a less than log b. No, I won't. Fix alpha between 1 and infinity, open interval. Determine sup c for c defined the same way as b. There is no upper bound of c. Suppose to the and for the proof, suppose to the contrary that b is an upper bound of c. I drew a similar picture here. If alpha is greater than 1, you can keep multiplying it by itself until eventually we get to be bigger than b. And that's going to contradict. We want to pick a natural number such that alpha to the n is greater than b, which means b is less than alpha to the n, if and only if log b is less than n log alpha, if and only if log b over log alpha is less than n, if and only if n is greater than log b over log alpha. By a similar argument to the last one, we can pick an n big enough that this is true. Thus, b is not an upper bound of c, which is a contradiction, since we started by supposing that there is an upper bound. That leads to a contradiction, so there's no upper bounds. Prove the infimum case of theorem 1.24. This is supremum and infimum analytically, which becomes useful in an exercise later. But the theorem is, let A be a subset of the reals, then the infimum of A is equal to beta, if and only if beta is a lower bound of A, and given any epsilon greater than 0, beta plus epsilon is not a lower bound of A. So maybe I draw a real number line, and I say we've got our set A. Let's maybe just call it like a closed interval. And we're saying that we have an infimum, beta. This is the infimum, implying that anything over here, if I pick something over here, then this guy is not going to be a lower bound of the set. So for any epsilon greater than 0, beta plus epsilon, that means anything over here, and a small enough a window as you want, nothing works. None of this is a lower bound of the set. Let's go ahead and prove it. Let beta be equal to the infimum of A. Okay, then beta is a lower bound of A immediately. That's pretty easy. Next, let epsilon be greater than 0. Okay. If beta plus epsilon is a lower bound of A, then beta is not the infimum of A, since beta plus epsilon is greater than beta, and beta plus epsilon is a lower bound. Thus, there is some x in the set A such that x is less than beta plus epsilon. Okay? That proves that for any epsilon greater than 0, beta plus epsilon is not a lower bound of A, because we found something in the set that's smaller than beta plus epsilon. Okay, now we have to go the other way. So we assume beta is a lower bound of A, and for any epsilon greater than 0, beta plus epsilon is not a lower bound. Okay. So we have to show that beta is a lower bound of A and that it's the greatest one. Beta is a lower bound of A immediately by this supposition. So that's pretty easy. Now we have to show that every lower bound of A, for every alpha that's a lower bound of A, beta is greater than or equal to alpha. So suppose there is some alpha that's a lower bound of A such that beta is less than alpha. Then alpha minus beta would be greater than 0. By supposition, beta plus alpha minus beta should not be a lower bound of A. Since this is greater than 0, and we assume this, but beta plus alpha minus beta is alpha, which is a contradiction, because this was assumed to be a lower bound, but it can't be a lower bound, which is a contradiction. So the theorem holds. That's not right. I need to go ahead and switch over to my unlined paper. Exercise 1.29, prove that the supremum of that is that, and the infimum of the same thing is that. So I guess I started with 1 is an upper bound of the set A, where A is this set. These are the same sets, so I just let A be the set. So to prove something's a supremum, you got to show it's an upper bound. 2 things we know about the supremum of a set: it's the upper bound and it's the least one. 2 things. So I start with 1 is an upper bound of A. If I let n be a natural number, then n over n plus 1 is less than or equal to 1 if and only if n is less than or equal to n plus 1, which is true. So 1 is an upper bound of A. Now, I let some A less than 1 but greater than 0, because we have no hope of something less than 0 being an upper bound. So I'm just going to pick it to be between 0 and 1. Let some a less than 1 be a real number. And we want to show that there's a natural number such that a is less than n over n plus 1. Okay? That means n over n plus 1 is greater than a if and only if n is greater than a times the quantity n plus 1. If and only if n is greater than an plus a, just distribute the a. If and only if n times 1 minus a is greater than a. So what I did was I subtracted an, and then I pulled the n out to make it n times 1 minus a. And we can pick an n big enough for this by the Archimedean property. Therefore, a is not an upper bound of a, thus 1 must be the supremum of a. Next, to show that 1/2 is the infimum of this set, first I have to show that 1/2 is a lower bound of the set. If I let n be a natural number, then 1/2 is less than or equal to n over n plus 1 if and only if n plus 1 over 2 is less than or equal to n. This is true. I proved it by induction. We went ahead with the base case. 2 halves is less than or equal to 1. That's true. 1 is less than or equal to 1. Now I went ahead and supposed that k plus 1 over 2 is less than or equal to k. We want that k plus 2 over 2 is less than or equal to k plus 1. And this is true if and only if k plus 2 is less than or equal to 2k plus 2. So, k plus 1 over 2 is less than or equal to k, supposition. Then, k plus 1 is less than or equal to 2k, just multiplying both sides by 2. Then, if I add 2 to both sides, this becomes k plus 3 is less than or equal to 2k plus 2. Now, k plus 2 is going to be less than or equal to k plus 3, so k plus 2 is less than or equal to, by transitivity, 2k plus 2, which is true, which shows what we wanted to show, which means that 1/2 is a lower bound of the set. Okay? We also have that 1/2 is in the set. So we have, this set has a minimum. Therefore, it has an therefore, the infimum is equal to the minimum. That's true for every set. So that's that done. 1.3. Let a and b be subsets of the rationals, and suppose sup a is less than sup b. Show there is some b in b such that b is an upper bound of a. Okay, I went ahead and, by contradiction, suppose no such b exists. That means for every b in big B, b is not an upper bound of a. Thus, there exists something in a such that a is greater than or equal to b for all b in b. And I kind of like justified this a little bit. No b is greater than or equal to everything in a, so something in a must be acting as a blocker of sorts. So if there were nothing in a that were at least everything in b, then something in b would be at least everything in a, which would contradict our assumption. Okay? But we also know that sup a is an upper bound of b. Since sup a would be greater than or equal to a, which would be greater than or equal to b. Since a is also an upper bound of b, then sup a is at least sup b, contradicting sup a less than sup b. So some b as originally desired must exist. And part 2 is to give an example to show this is not necessarily the case if only sup a less than or equal to sup b. I let the two sets be equal to the open interval from 0 to 1. Then sup a is less than or equal to sup b, but nothing in 0, 1 is an upper bound of 0, 1. Okay, 1.31. Suppose that a and b are subsets of the reals, they are non-empty, and they are bounded above. Find a formula for sup A union B and prove it is correct. I came up with sup A union B equals max sup A sup B. And I'm going to go ahead and prove it's correct. Let A equal sup A and B equals sup B, and let X in A and Y in B be generic elements. Then, there are two cases, A greater than or equal to B, or B greater than or equal to A. I just did the one case, A greater than or equal to B, because the argument's the exact same the other way. So maybe you can go ahead and try the other way as an exercise. I did the thing where I left it as an exercise to the... If A is at least B, then we have A is greater than or equal to B is greater than or equal to Y, which is something in B. It's a generic element in B. Thus, A is an upper bound of B. A is also an upper bound of A, since A is sup A. Now, we let C be an upper bound of A union B. Then, C is an upper bound of A, so C is at least A, which is equal to sup A. So, A is equal to sup A union B, because any other upper bound of A union B is at least A. Since A is greater than or equal to B, max AB also equals A, which is sup A union B. The argument is similar the other way around. We just have to use the other generic element, and it's the exact same, so don't worry about it too much. I wrote this one down on line paper. This one is, the second part is a little bit of a doozy, but we'll get to there. Suppose A is a subset of the reals, it's bounded above, and C is a real number. Prove that the supremum of C plus A is equal to C plus the supremum of A. Maybe I should define this, where C plus A is the set of everything C plus A such that A is in A. So we just took the whole set and we shifted it by C, basically. I let A be equal to sup A, just so that I don't have to write sup A. I can just write A. Then C plus sup A is equal to C plus A, and I let X be a generic element in A. A is greater than or equal to X, since A is the supremum of A. So C plus A is greater than or equal to C plus X, which means C plus A is an upper bound of C plus cap A. Okay. Now, I have shown that C plus sup A is an upper bound of C plus A. Now I have to show that it's the least one. So I let alpha be a generic upper bound of C plus A. C plus cap A. Then, for any beta in C plus cap A, alpha is greater than or equal to beta. We want alpha greater than or equal to C plus A. Since alpha is greater than or equal to C plus Y for all Y in A, then alpha minus C is greater than or equal to Y for all Y in A. So alpha minus C is an upper bound of A. Since A is equal to sup A, alpha minus C is greater than or equal to A, so alpha is greater than or equal to A plus C. So alpha is a generic upper bound of C plus cap A, and it's at least A plus C, which means A plus C is equal to sup C plus A. Now, to determine necessary and sufficient conditions on C and A so that sup CA equals C sup A. This is defined similarly. CA is defined as the set of all elements C times A, such that A is in big A. So we scaled the whole set by C, if you will. This one's asking you to construct something. It's asking you to construct conditions on C and A so that this thing holds. So I went ahead and went with some sufficient conditions. If A only has one thing in it, then the supremum of the set is going to be the thing. And C times the thing is going to be C times the thing. C times the set is also going to be the singleton set containing C times the thing. And the supremum of that set is going to be C times the thing. Okay? We also have, if C is not negative, then sup CA equals C sup A. I don't seem to have proved that on this paper, so maybe you can go ahead and see if you can prove that one too on your own. I'm giving you a little bit of homework, but write down it in the comments if you want me to prove everything I say or leave some stuff. And make sure to subscribe. Let that subscribe button be greater than 0. So if sup CA is equal to C sup A, that means CA is equal to sup CA, or I just let A be equal to sup A. And I let alpha be a generic element of A. A is at least alpha, because A is the supremum of A. Also, since CA equals sup CA by supposition, CA is at least C alpha, which means CA minus C alpha is at least 0, which means C times A minus alpha is at least 0. Which means either C is greater than or equal to 0, or A minus alpha equals 0, which means A equals alpha. Since alpha is a generic element of A, if the supremum of A equals a generic element, then the supremum is equal to every element. One thing can't be equal to two things that aren't equal, so there must only be one thing in the set. So either C is not negative, or A only has one thing in it, which gives us our cardinality of A is 1 or C is not negative. This actually gives us our double arrow, which is what we wanted. Suppose A is not empty and A is bounded below. Prove negative A is not empty. Negative A is bounded above, and the supremum of negative A is negative E infimum of A, where negative A is negative A, such that A and A. So we flip it around the x-axis, if around the point 0, if you like. A is not empty, so there is something in A. So negative x is in negative A. So negative A is not empty, because there's something in it. Brilliant. Wonderful. A is bounded below, so it has a lower bound. Alpha is less than or equal to A for every A in A. That means negative alpha is greater than or equal to A for every A in A, which means negative alpha is greater than or equal to A prime for every A prime in negative A. Thus, negative A is bounded above. Now, suppose A equals sup negative A, then A is greater than or equal to alpha for every alpha in negative A, which means negative A is less than or equal to negative alpha for every alpha in negative A, or negative A is less than or equal to alpha for every alpha in A, which means negative A is a lower bound of A. You might see where this is going. We proved negative A was a lower bound of A. Now we're going to prove it's the infimum. Since A equals sup negative A, there is no A prime that's real, such that A prime is less than A, and A prime is an upper bound of negative A. If we suppose some real number beta exists, such that negative A is less than beta, and beta is a lower bound of A, then beta is less than or equal to alpha for every alpha in A, because beta is a lower bound. So negative B is greater than or equal to negative A for every alpha in A, which means it's greater than or equal to alpha for every alpha in negative A. But negative A less than beta, so negative beta is less than alpha, which is a contradiction. A equals sup negative A, so negative A must be inf A. So A equals sup negative A equals negative inf A. Wait, why? Oh, because, right. This is a contradiction because then negative beta would be a lower upper bound of negative a than a. Okay, that makes sense now. I was looking at that for a really long time. I'm not sure if I'll put a think timer on that one because that was an egregiously long time. Okay. 1.34. The so-called nested interval theorem. Where is it? I didn't write it down on unlined paper. Unlucky me. So here it is. For each n, that's a natural number, we're given a closed interval from an to bn, where I went ahead and assumed that an was less than or equal to bn to make it a good interval. And we assume that in plus 1 is contained inside in. This gives us a sequence of increasingly smaller intervals. Okay, so we start with I1, that's our biggest interval. I2 is contained in that one. I3 is contained in that one. I4 is contained in that one, and yada, 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 off to infinity. Prove that the intersection of all the intervals is not empty. That is, prove that there is something in it. And if something is in this intersection, then it's in in for every natural number. So I went ahead and did that. Wait, what? Where's the paper? Oh my gosh. I didn't... All right, we're going to do this one live. 1.34. We have in is an bn for every natural number, and in plus 1 is contained in in. So this gives us I1, which contains I2, which contains in, contains yada yada. Prove intersect n equals 1 infinity. In is not empty. We're going to show there exists something in the intersection. Actually, we're going to show that an entire interval is in the intersection. So we're going to start off by considering two sets. Consider the set of all left endpoints of intervals and the set of all right endpoints of intervals. Since a1 is less than or equal to b1 and in plus 1 is contained in in, this means that an is less than or equal to b1 for every n in n, and similarly a1 is less than or equal to bn for every n in n. So I'll call this A and I'll call this B. So A is bounded above and B is bounded below. What do we know about sets that are bounded above or below? We know they have supremums or infimums respectively. So sup A and inf B exist. Call them alpha is sup A, beta is sup B. Okay? Fantastic. How does this help? Well, what I'm going to show is that the closed interval from alpha to beta is actually in the intersection. And what needs to happen is I need to show alpha is less than or equal to beta. So if we suppose to the contrary that alpha is greater than beta, since R is dense in itself, then there is some gamma that's real such that it's between them. Gamma is not an upper bound of A or a lower bound of B. So there exists A in A and B in B such that alpha alpha is greater than A, which is greater than gamma, which is greater than B, which is greater than beta. Gamma is not an upper bound of A, so there's something in A that's bigger than it, and that's what that means. Similarly, there's something in B that's smaller than gamma. This is obviously contradicting AN is less than or equal to B, I guess BM even, for all N, M that are natural. Okay, so we must have that alpha is less than or equal to beta. Let's see if I can fit this on the last line here. So for any I that's natural, AI is less than or equal to alpha, because alpha is the supremum, which is less than or equal to beta, which we just showed, which is less than or equal to BI, which is, because beta is the infimum, which means that this is in II for every I in N, which means, can I fit it? Alpha to beta is in the intersection of IN box. I fit it. I skipped a lot of lines that I didn't need to skip, but we did it. We got there. That was it. That was a live solve. 1.35. Give an example where this fails if we only have that, or rather if each IN is allowed to be open. So I define IN to be the interval from 0 to 1 over N. Then every interval is contained in the previous interval. And if we pick any x in 0 to 1, we know by the Archimedean property there is some n such that 1 over n is less than x. So x is not in the kth interval for every k greater than n. X is missing from at least one thing, so it's not in the intersection of all the things. This is true for every number in 0 to 1, because we picked a generic element and we showed that this was true. So since there's nothing in the intersection, it must be empty. Home stretch, there's only 2 more. 1 more? 2 more. Determine 135 plus negative 301, where we just, this is defined the same way as it was the other time. We just, element-wise, add everything together and make a new set out of them. You can go ahead and verify that this is true if you want. I'm not your dad. Part B is to assume A and B are subsets of the reals, and sup A and sup B exist. Prove sup A plus B is sup A plus sup B. Okay, so did my old trick, let A equals sup A, B equals sup B. We want to show A plus B is sup A plus B. Here I showed that a plus b is an upper bound of cap a plus cap b. Let c be an element of cap a plus cap b. Then c equals alpha plus beta for some alpha in a and some beta in b. A is at least alpha and b is at least beta, so a plus b is at least alpha plus beta, which is c. So a plus b is an upper bound of cap a plus cap b. And I tried to show it was the supremum by showing that every other upper bound, or that every upper bound was at least a plus b. That didn't end up working out for me. So I went for suprema analytically. And Jay Cummings has very sneakily got us to think analytically by having us combine two different things that have epsilon in them. So here's what's going on. Because of suprema analytically, a minus anything positive is not an upper bound of cap a. Okay? That means if I let epsilon be greater than 0, then there is some alpha 1 in cap a such that alpha 1 is greater than a minus epsilon over 2. Since epsilon over 2 is still positive. Okay? Similarly, there's a beta 1 in b such that beta 1 is greater than b minus epsilon over 2. Okay? That means alpha 1 plus beta 1 is greater than a plus b minus epsilon. Alpha 1 plus beta 1 is an element of cap a plus cap b. Thus, for any epsilon greater than 0, a plus b minus epsilon is not an upper bound of cap a plus cap b. Because I let epsilon be greater than 0, generically, any epsilon greater than 0, there is something in a plus b that's bigger than a plus b minus epsilon. And that is suprema analytically. Next, 1.37, very similar. We just have to compute 135 times negative 301. This is what it comes out to. And give an example of sets A and B where sup A times B is not sup A times sup B. Let them be the same set, two elements, negative 1, negative 2. Sup A is negative 1, sup B is negative 1. The supremum is 1. Negative 1 times negative 1 is 1. But A times B is 1, 2, 4. And the supremum of that set is 4, which is bigger than 1. And that concludes chapter 1. I'm going to leave in that live solve. If you really hated it, tell me, and I won't leave those in next time. And if you really, really, really hated the unlined paper, or maybe if you preferred the lined paper, tell me that too. That's it. I can't believe we're done. That's crazy. Now on to chapter 2, which is coming soon. I do have to read it and make the video going over the material it covered. But that is going to exist sometime. See you next time.